What's the rules? 30 minutes? Or
30 minutes.
30 minutes.
Plus 5 minutes per question.
Okay. So I'll try to even finish.
I'll show you the 5 minutes if you want.
After 20 minutes showing, because maybe I want to give them a little more time to react and then to continue with the slides after a few questions.
Yes.
אז זה קדימה?
קדימה, אחורה ולייזר.
Here is Abraham Neyman, who is going to talk about open problems in repeated games with finite automata.
Okay, thank you. Thank you for the invitation to speak in this conference. When I was young, more young than now, but I had the feeling that one of the objectives of workshops is to solve at least one open problem in the field. So I decided I'll present a few open problems, and I hope that by the end of the workshop somebody will solve some of them. And those who are interested in working on it, or some of those, I'll be happy to share more insight on what are the difficulties, etc. So the first two slides will tell you all, but later I'll elaborate with a few more details on what's going on. So first of all, I'll classify the open problems into two types. One is two-person zero-sum games. And here the question is to quantify the advantage of a larger automata in repeated games. And slightly more explicitly, if we would look on the repeated game that lasts for T rounds, and player one has to play a strategy that he could implement with an automata of size K1, and player two has to choose secretly or randomly a strategy that could be implemented by an automata of a deterministic automata of size K. So this is that repeated game. So here are these spelling that I just said. Number of repetition is T, which could be infinite, so we could speak of the finitely repeated game or the infinitely repeated game. Player I is confined to play a strategy that is implementable by a deterministic automaton of size Ki. Obviously, he could decide of taking some lottery between these machines. We don't know which one of the strategy he has chosen, so it's like thinking that he's playing a mixed strategy where each realization of the mixed strategy is a strategy that could be implemented by a deterministic automaton of size Ki. And the payoff in the repeated game, we are looking for the average payoff per stage of the game. So basically, we want to study what is the behavior of the value of this game, every two-person zero-sum game as a value. We could look on the value as a function of those three parameters and look on its value when K1, K2, and T, the triple, goes to infinity. Then there is the question in the Nonzero Sun, which captures slightly different issues. And here, we just want to quantify the equilibrium payoff of the non-zero sum game, repeated game with large automata. So we think of the automata of being large but finite. Sorry, I'm saying finite not necessarily, but later on. So explicitly, what is the asymptotic behavior of the equilibrium payoff of the game that repeats for T rounds? Player I as restricted to play with a strategy of size, of an implementable by automata of size Ki, and we look on all these terms going to infinity, and we want to study what is the equilibrium of. So let's just make sure, I assume that most of you are familiar with strategies that are implementable by finite automata, but let's go back with one slide on this concept. I'll come back to the zero-sum game. It's just the first two slides that go a wish on the entire lecture, and then I'll spell out. If you allow all strategies, yes. But if I know that you are playing some deterministic strategy with an automata that has 5 states, I don't know the program that you put on your machine, but I know that it has that many states and doesn't take within its play any lottery, I could try to guess its play. So if I have an infinite size automata, eventually I would learn how you are playing and I'll beat you every round. So the question is how big I should be so that I could outguess the output of your automata. What should be the relations between the sizes of the automata? So the finite automata strategies, we have the game. So we have the set of players. We have each player as an I as a set of actions, and we have payoffs separate for each action. So that's the set of players. AI, the actions of player I. GI is the payoff. Now, what is an automata? An automaton for player I is a 4-tuple that consists of a set of states S with S1. S0 equals S1. S1 in S, the initial state. The size of an automata is the number of states in the machine, so it's the number of elements in S. Then we have an action function that determines deterministically which action the automata or the player that is using this automata to define the strategy will take as a function. And then we have a transition function, which you are in a given state of your machine in a coordinate here in S, and you observe some action of all the players, and then you decide what is going to be your next state. Obviously, you will see in the literature that often this second coordinate is being defined only as functions of the actions of the other players, but it is basically the same because your own automata specifies which action you have taken at the state S. So if you know the actions of the other players, you could incorporate also your own actions, so you have such a function. And then, what is the strategy that is being defined by this machine? So, at the first day, it takes an action, which is just the action function. I switch notation. F is alpha. Yes. So this alpha and this F is the same. So it is alpha of the first state. And after k many stages, if you observe the history A1 up to AK, a strategy has to decide which action to take then. So it takes the action alpha of SK, where the new state, so in order to define that, I have to define SK as a function of the previous ones. And SK is simply the transition function from the previous states together with the last action tuple that is being observed. Is it clear what is the strategy that is defined by a finite automata? Because all the remain, if you miss that, it will be difficult to follow. And now we are coming to the open problems. Okay. So the first one. You look on the values of this game. So when I put out the duration t, I mean the infinitely repeated game. Player 1 is restricted to an automata of size k. Player 2 is restricted to an automata of size k. And the question is, does it converge when the log of the larger, nk, is the automata of size? Because of duality in two-person zero-sum game, I could always assume that the second player automata is larger than the first one. So if the log of the larger one over the smaller one converges to x, you can obviously ask yourself, why the log? Why not another function? Why this is the right order of magnitude? And we'll see in a moment why this is the right order of magnitude. But first of all, for those values of x for which it converges, and my conjecture is that it converges for every x, what is the function of this value, of the limit of these values when k goes to infinity? So is it true that for large automatas, the advantage of the stronger player is some function of the stage gain, g, and the ratio between the log of the larger automata to the smaller automata? And why is the scale this one? Because there are exact asymptotics for the case x equals 0, when Porat 93, basically 86, but published in 93, computes this limit of the value. Let me right now tell you that it's the value, in this case, when x equals 0, it converges to the value of the stage gain. For x sufficiently large, yes, larger than this the log of the minimum of the sizes of the matrix. So if it's matching pennies, so the size of actions of each player is 2, then its log is 1. So it means for x larger than 1, it is known the exact asymptotic, what it is. And what it will be in matching penny, it will mean that for such automata, you will be able to guess exactly the output of the other one. So you come to the max, to the min-max of the stage game in pure actions. And this was extended also for this boundary point, exactly when it is this low, by myself and Spencer. And what happens in between is not clear. There is some lower bound, some function of x that could be described as the lower bound of this limit. So for this region between those two extremes for which we know the answer. And let us now, instead of nailing, when I like to give an open problem, this was very general, all games and so on. Let me pinpoint a specific game, tell you the data on this specific game, tell you a very explicit open problem on that. And I am promising a good dinner in the best Jerusalem restaurants for those who would solve it. So the game is the matching pennies. I just switched the numbers to be all positive. So it's 2, 0, 0, 2. So player 1 tries to guess the action of player 2. If he guesses correctly, he gets 2 units. If he misses, he gets 0. And player 1 tries to maximize. Player 2 tries to minimize. You remember player 2 as a larger automata. So I assume that in this crowd, everybody knows information theory, log. So I'll skip it. If you want, I'll come back. Should I go quickly on it? The formulas, okay, I'll go. Yes. First of all, and it turns out also, if you see a log, it's natural that it's related in some way to entropy, combinatorial entropy if you're just counting, so probabilistic entropy. And indeed, you will see that the formulas itself, in the case that we know something, are expressed with the aid of the entropy function. So it's likely that it will enter into the solution. So a quick review of the entropy, what's relevant here at least, is that the entropy of a random variable that gets the value 0 and 1 with probability p and 1 minus p is this specific formula. And the graph of this probability is drawn in this picture. So you see how it's strictly concave, smooth function. The maximum is in the middle, goes down to 0. So now I'll give you in a picture what we know about this particular game, the matching penny. So this is a graph, which is the lower bound. Here, it's the exact limit, let's say, when x is 0. So this is the log n, the log of the bigger one divided by the smaller one. So this is known here. And basically, just to repeat, the case x equals 1, x equals 0. The special cases in the previous case are these two results, x, oh yes, okay. And in between, this is the lower bound of the limit. So the limit inf is above at least that. And my question is, what is it for every particular x for this particular game? But explicitly, let me give you one specific problem. X equals 1/2. So if the larger automata n is to the size 2 to the power k over 2, that's the size of the bigger automata, how much advantage he could have, how much he could push down from the value towards the min-max in pure actions. Oop. 1. An upper bound is 1. I could do a little better than 1, okay? So it's, if you go, I could draw you some function there that is below 1. In this case, okay? But very close to 1. It means there is still a big gap.
Do you have conjecture? Do you conjecture this is the truth?
I'm afraid to make here a conjecture.
Don't be afraid.
No, no, no. I don't have a firm conjecture. Yes, my conjecture will be, and this is the trivial conjecture. It's almost automatically, if the limit exists, it is true. Is that there is some positive transformation of x, yes, such that after I adjust this formula with this positive transformation, this will be the limit. So that's trivial in a sense. But what I think is that this transformation should be easily written. It means that there should be a simple formula for this transformation, not just to say that's a limit. So there is one candidate, it's that function. There is one other candidate, which is some iteration of it, which is well defined, and so on. So it should be related to this function. How exactly, I don't know. Oh. Okay, open problem number 2. Before, we looked on the infinitely repeated game, and we just compared the sizes of the two automata. Okay? You could also say, let's even study the following question. One is unbounded. Basically, if you could play with an infinite automata, you could play any strategy. The other one is bounded. So we know from the previous results that the infinitely repeated game, you will eventually outguess him at every round. The question is how long it takes. And so what is the function of how long could a weak player with a fixed automata protect himself as a function of the duration of the time? So does the limit, the values of these games, converge when k goes to infinity, and the log of the duration divided by k log k, yes, here missing a k, tk divided by k log k converges to x. You could ask the same question, why this is the right scale? Maybe it's a completely different scale, and here I don't have a good answer, okay? But just there is a conjecture that if the conjecture is true, this is the right answer. So for those values of x which the limit exists, what is the limit as a function of the stage game g and x? And exact asymptotics is known, so this is when this x goes to infinity, when x equals to infinity, then it means that the smarter player could bring the weaker player to the min-max in pure action. So he could eventually guess him in most rounds of the game, he could guess exactly the action. And the conjecture is that if it is equal to 0, then the smaller player, the weaker player, could protect the value. Then it converges to V. So here, if this will be answered, then this will be the right scale. Otherwise, I even don't know if that's the right scale. Yes. What happens, for instance, even, because this is an open conjecture, what happens, for instance, if the number of duration is just 10 times the size of the smaller automata? Obviously, there is one trivial case. If the size of the duration is less than k, then there is no problem. You could play any mixed strategy that you want, because you could play any sequence, any periodic sequence of period less than k, you could play, and therefore you could play any probability distribution over this type of sequences, and if the duration is less than k, you could protect your value. But the question is, what happens if the duration is more? Let's say 100 times k is t, I don't know the answer. My conjecture is implied by this conjecture, and the conjecture is that this is the, yes? Yes. Okay. Yes. There are few refinements that maybe later, if there will be question and there will be time, there are even more slides that will tell you this type of fine-tuning. But you could refine this question even with pure strategies. Yes. And even with pure strategies, it is there are issues that are, if you restrict the class of strategies to pure rather than mixed in this type of models or other setups, there are. Okay, what's the open problem in non-zero-sum games? And here again, the general question, as was said before, is what is the limit behavior of the equilibrium payoff of the T repeated game could be infinite, could be finite, when the size of the automatas of the players are k1 up to kn, when the duration of the game and the sizes of the automata go to infinity. And let me say that this is well known, not well known, but that's known, for two-person games. Two-player games, the result is known. Both for the T equals infinity, it follows essentially from the two-person zero-sum theory. And for T finite, for example, the finitely repeated prisoner's dilemma, it requires some work, but it's completely solved, and you get results like the Folk theorem. So in the general case, when it's more than two players, then for the case T equals to infinity, the essential issue is the individual rational level. And for T less than infinity, if there are more than two players, we say in two players it's completely solved. There are additional issues that if some of you have started to study the 2 case or are familiar with that and have questions, I'll answer it in the question. What are the questions there? But let me show two specific examples that illustrate these difficulties of the individual rational level and the equilibrium. So first of all, for the individual rational level, if you look on this 3-player game, if you look on this 3-player game, so only in these cells, okay, I wouldn't try to point because it's right. So here what will be important is our player, essentially it's almost a two-person zero-sum games between player 2 and 3 and player 1. So they would like basically to maximize the probability of hitting one of those two cells where the payoff is 1. So in a one-shot game, if they take two independent strategies, then one of these boxes will have, one of these matrices will have probability at least half and half, at least 1/4. So basically, the player could protect and guarantee that he would not get a payoff below -1/4, if I'm not wrong. But if they could have correlated it, if they could have played player 2 and 3 left and this matrix, so player 3 chooses the matrix left and this matrix with probability 1/2, or right and this matrix with probability 1/2, then they would guarantee that they get a payoff of at least 1/2 each, and that the other player gets a payoff of no more than -1/2. So they want to do that, but for that they have to correlate their actions, but they are choosing independently their automata. So the question is how two independent machines can generate eventually a correlation that is concealed from this player 1, so that it will be viewed by him as if they're playing with some high probability left east or right west, and he couldn't distinguish this correlation between the two other players. So there are some results in this direction, not much for the model of finite automata. And an illustration of the case of the finitely repeated games is if you look on T equals infinite, this is a 3-person prisoner's dilemma. And if you would like to think how can you sustain in equilibrium the payoff 2 to 2, which is the cooperative equilibrium, when let's say that the size of the first automata is T, the size of the second automata is 2 to the power square root of T, and the size of the third automata is 2 to the power 1/10 of T. Can they, under what condition, yes, of those orders of the 3, they could attain cooperation. I could tell you that this is, I think I know the result. Yes, I think I wrote myself notes for the proof, but it's unpublished. So if somebody decides to publish it or solve the general game, that's fine with me. But this is an issue, and it goes behind the solutions of the two-player games. I'm wondering if to show the rest slides now or after as a result of the question, but I don't trust that you'll ask all the questions. So, yes? 10 more minutes for the talk itself. Oh, for the talk and the question. Okay. So let me ask a few questions. Okay? Assume you are asking the question. So first of all, you know, all the model that I was studying here is finite automata, and this was also in the title. There are some very simple structures, finite automata. One is an oblivious automata, an automata that doesn't look on the actions of the other players. If an automata of size k is playing and it doesn't observe the other actions, essentially his actions will enter into a cycle which is of length less than k. So he could decide on what is the length of the cycle and what is the actions in this cycle, and it could take a lottery over all these actions. This is one family of automata. Another family, we call those oblivious automata. Another family of automata will be the bounded recall strategies. And even though when I want to say finite memory, when I say finite memory, I mean finite automata. Yes, and we had a discussion of that some time ago, and finite statistics or finite memory is finite automata, not finite recall. Herb Robbins was written one paper in the early 60s or late 50s on statistics with finite statistics, and he was talking about finite recall. And Carver and others later told him, look, the right model of finite memory is not finite recall, but finite automata. Nonetheless, finite recalls are important, and if we will understand finite recall, we might get some insight into the finite automata literature. So let me tell you that if we look on some of these variations, then there is exact asymptotics for the model of the two-person zero-sum game when player 1 is restricted to oblivious automata and player 2 can play an arbitrary automata. Essentially, the limit is, in that case, the lower bound that we drew in the picture for the matching pennies. And you could draw this function for any game, and the exact asymptotics follows from some result of mine and Peretz. Peretz essentially improved significantly the dependence on t. That, initially, I knew that only for some values of t. And if you look on the asymptotics, in the case that there is k recall for player 1 and n recall for player 2, an arbitrary t, but you look on the asymptotics, there is an exact asymptotic theory developed by this guy, Ron Peretz, and beautiful results. Encourage each one of you to read. Maybe it will serve as some insight also how to solve the thing with the finite automata. Okay, any questions? Time for the questions? Okay. Yes?
It seems for me that these questions are strongly related to the pseudo-random generating. Do you know something about it? Maybe its connection?
In a sense, it's a kind of an interactive pseudo-number generator, but here you want to generate the pseudo-number with a finite memory. Yes. The issue here, maybe another, yes, does it answer? Or? The question is how to generate something that would look random to another machine, but you want to generate it with some simple machine of yourself, a simple program, an uncertain program on your machine, and you know that the other machine is bounded in its size. Any other question? Yes?
On finite automata, what about more general models of computation, like Turing machine, Boolean series, etc.?
There are other models. I think with Turing machines, it will be essentially impossible to get any quantified results. Yes, that's my feeling. Obviously, it's of interest to see what one could do there. If you look on another model of Kolmogorov complexity, then you could get nice, in some of these setups, you could get nice asymptotic results. But with Turing machines, I don't know of any explicit result that gives a rate of
Thank you.
Sorry.